So I'm going to go through the notes for Unit 5A that correspond to Moodle Quiz 1. So first, let's make sure we understand the difference between kinetic and potential energy. Kinetic energy is the energy of motion and is calculated by taking 1/2 the mass times the velocity squared. The potential energy is the energy in an object that is stationary, and it would be equal to the mass times gravity times height. The law of conservation of energy states that energy cannot be created nor destroyed. So, however much energy there is before, there must be an equal amount of energy after. So you may have, for example, a ball that's suspended in the air, and so right now it possesses potential energy, which is mass times gravity times height, and 0 kinetic energy. But once that ball falls to the ground, then the energy is converted to kinetic energy, which is 1/2 mass times velocity squared, and the potential energy becomes 0. So throughout this entire process, from this point to the point where it drops and hits the ground, the potential energy, mass times gravity times height, must be equal to the kinetic energy during the process of falling, 1/2 times mass times velocity squared. The velocity just before impact could be determined by taking the square root of 2 times gravity times height, which is basically simplifying this equation to set it to solve for velocity. In thermochemistry, we focus on energy in terms of heat or work. So work is equal to force times distance, and in the world of chemistry, we're going to look at the work that a gas does when it expands or contracts. So we calculate work by keeping pressure constant and using the change in the volume. Temperature has a direct correlation to energy. So if you increase the amount of energy, then you also increase temperature. Gas volume, if we recall, is PV equals nRT. So if I rearrange this to solve for delta V, volume, then I get the moles times the R times T divided by the pressure. Volumes of solids and liquids are negligible to that of a gas, so we really only focus on changes in the volume of a gas. Work of expansion. So work is equal to negative pressure times the change in volume, and we can determine the change in volume using the gas equation, which is equal to nRT over P. So in a chemical reaction, you may have a change in volume as a result of a change in moles from total gases of reactants and total gases of products. So to calculate the delta N, it would be the change in moles of gases only in a reaction, and you would take the moles of gases as products and subtract the moles of gases as reactants, and then you would have the change in moles. And then times RT over P would give you the change in volume that occurs with that reaction. We're going to use the gas constant 8.314 joules per mole Kelvin for R because work is in a unit of joules. So we're focused in energy. Heat moves from hot to cold. Here's a scenario we're going to look at. Let's say you have an object hanging here. And once that object is released, then the potential energy converts into kinetic energy. But what happens when the object hits the ground? Well, some of the kinetic energy is lost into the ground in the form of heat. Upon impact, the kinetic energy from the object will transfer a little bit into the molecules in the ground, causing them to vibrate, which is considered energy in the form of heat. Which is why, say, if this object were to bounce, then it would slowly lose more and more energy until it comes to a full stop. Or if this object were to hit the ground and stop abruptly, then all of the energy would be transferred from the object into the surroundings as heat. Let's make the distinction between the system versus the surroundings. The system would be, say, a chemical reaction or an object or a system where you're dissolving a salt and water. So the system is what we focus on, and the surroundings is everything else around it. There are two types of systems. An isolated system, which is so closed off that matter cannot enter the system, neither can energy. And then a closed system, which is more common, where matter cannot enter, but energy can. And usually it's energy in the form of heat. So the abbreviation for heat is going to be Q. and the abbreviation for work is W. So if we look at a system, if work is done on the system, so imagine this were a balloon, but let's say that we have external pressure pushing the balloon to become smaller, so it's contracting. Then you could say work is being done on the system or on the balloon, and so that would be a positive amount of work. If heat is absorbed into the system, which is endothermic, then you also have a positive symbol for heat. The opposite, if the system is, say, expanding outward and doing work on its surroundings, then you have a negative for work. And then if heat is released from the system into the surroundings, it's exothermic, and so you have a negative value for heat. So here, W is positive, Q is positive, and here W is negative, Q is negative. Now, anytime a solid converts to liquid and a liquid converts to gas, these are endothermic processes. So a solid has to absorb heat in order to convert into a liquid, and a liquid has to absorb heat in order to turn into a gas. The opposite of that is if a gas turns into a liquid, it has to release energy, and that's an exothermic process. Liquids changing into solids also have to release heat in order to do so, and so it's exothermic. Consider the process of cooling a gas and heating a gas. So here, let's say I have the gas is the system, and let's say we're going to cool the gas. And by cooling the gas, it causes it to shrink inwards or to contract. And so the system has a positive amount of work being done. The surroundings are pushing the gas inward, so the system has work being done on it. And cooling requires the system to release heat energy to the surroundings, and so it's exothermic, which means Q would be negative. So notice the signs are opposite in this case. If I am heating a gas, causing it to expand, the gas will then do work on the surroundings, which is going to be considered a negative amount of work, and it has to absorb heat in order to expand, and so that's going to be an endothermic process, which means Q is going to be positive in this case. So a state function means you will have the same result regardless of the path that is taken, and a path function is path dependent. So for example, if you had a chair and a table, and there are two ways that you could say stand on the table. You could jump from the ground all the way up to the top of the table, that's one path, or you could take the chair, step up on the chair, and then step up on the table, and that's a second path. So there are two different paths to get there. However, the state function would be the fact that you are ending up on the table. So regardless of which path you take, you end up at the top of the table. However, the number of steps you take is going to be, say, your path function, where you either do it all in one step or you do it in two steps using a chair. So each of these, mass, delta E, delta H, Q, delta G, delta S of a system, temperature, pressure, volume, all of these are state functions, meaning it doesn't matter how we get there, we only care about the end result. These are path functions, time, heat, and work. At constant volume, work is going to equal 0. So meaning if there's no expansion or contraction, then no work is being done. So work must equal 0. At constant pressure, the enthalpy is equal to the amount of heat energy. So delta H is equal to Q. The first law of thermodynamics states that energy is conserved, and so here's an equation for that. The delta E, change in energy, must be equal to the heat plus the work. At constant pressure, delta H can be substituted for the Q. Delta H is the heat of reaction, which expresses whether or not a system is endothermic or exothermic. Anytime there is a system where dissolving is occurring, the delta E, change in energy, will be 0, and the delta V, change in volume, will be equal to 0.